Oh,
Okay, shall we start, Ray?
sure, let's go.
Okay, great. So, good morning, everyone. Welcome to our ICMR Research Seminar Series, session 54. And today we're honored to have Professor Raymond Friedman from Vanderbilt University. And he's gonna give us a very interesting, cutting-edge research topic that is building an AI model for transcript coding, enhancing capabilities for negotiation scholars. So I was lucky to attend the Ray's PDW last IACMR in Hong Kong, and I got a chance to know some very cutting-edge research regarding the application of AI technology in the negotiation research. So I really look forward to today's speech. And although everyone is very familiar with Ray, but I still want to give a brief introduction to Raymond Friedman. And Professor Raymond Friedman is now in Vanderbilt University, and his research has included in negotiation, dispute resolution, and management of diversity, and also some cross-cultural research between Chinese and American managers. And his work has appeared in many top-tier journals, including ASQ, MJ, JP. And Professor Raymond has served as the president of IACMR and also the president of the International Association for Conflict Management, and also as the chair of the Conflict Management Division of the Academy of Management. So before we move on, I also want to promote our 11th biannual IACMR conference that is going to be held in a beautiful city, Xi'an, this June 11 to 15th. And if you haven't registered yet, I strongly recommend you do so as soon as possible to enjoy the early bird registration fee. And this year, we are going to have seven keynote panels, 22 symposium, and 755 paper presentations, and 26 professional development workshops. And we committee members are working very hard now to prepare the final programs. And this year, there are going to be some new initiatives. For example, the Women Development Forum, and also men are welcome to register. And also, we have a happy hour session exclusively for students. So this is brand new. So if you haven't registered, please do it as quick as possible. Now let's warmly welcome Professor Raymond Friedman.
All right, good to hear from everybody, to see everybody. It's a few people I haven't seen for a long time. I'm very excited to be here and share this with you. Let me share my screen and get my slides up. And let me also confirm, is this an hour 15 or an hour 30?
It's an hour 15.
That's what I thought. Okay. The All right, so I've been working on a project that, if those of you who know me, I'm not the most technical person, but I kind of learned about AI modeling and some support that the Data Science Institute provides here at Vanderbilt to people around the university, and got connected with those folks, and have been working for several years now on applying AI tools and methods to problems that negotiation researchers face. And I hope that what I talk about will be relevant not just to those who study negotiation, but might be useful as a model for how to use AI in other areas as well. And I should start by saying one of my co-authors and the data science guru behind a lot of the technical stuff, John Shuhui, is on the call with me. From Vanderbilt. And Jean Brett might be on the call. I'm not sure if she's here. She is also one of the drivers of this project. And it's a project that is supported by NTR, Negotiation and Team Resources, which is run by Jean Brett, formerly of Kellogg. She's retired and she's emeritus. And a lot of data scientists, and then a lot of people who contributed data. So let me jump into it. To start with, to be clear, I'm building tools for negotiation researchers. not creating negotiation chatbots. And so there are a lot of people who are doing the chatbot areas of research. There was a conference at MIT last week that I was at where people are trying to figure out how do you get bots to, coach negotiators, to be agents for negotiators, be agents, be coaches of mediators. But I'm looking at research scholarship and providing some tools for them. And so the main thing I'll be talking about is coding transcripts. So, why would this be necessary? So a lot of researchers engage in a process, not all negotiation researchers do this, but some, where they will run simulations. There's people who get a buyer or seller role and they get confidential information. They're they're either subjects or students, um, and they engage in a negotiation. It's tape recorded, it's transcribed, and what you see on the right for a negotiation called Les Fleurs is a bit of transcript of that negotiation. And so what they would do typically is run the simulation, record conversations, and they would have a coding scheme to look at it. And there's many different coding schemes depending on the purpose and goal of the researcher at that for that project. And then you have a process of processing the data. So the first thing you do if you have a coding scheme is you teach several people to be trained in that coding scheme. You have them go through and code it, line by line or turn by turn. You check for agreement and make sure there's enough convergence in the opinion of the two raters that you can believe the code is accurate. And then you have that set of codes and you go and use the codes for some other broader question. The code is simply a vehicle to move into other questions. So maybe what you code is active listening, or maybe you code humor, or maybe you code sharing of interest-related questions. There's a number of things you might code. And you might then ask afterwards, what are the things that would happen prior to that that might predict the use of a certain kind of statement or technique? Or if someone uses humor or active listening, what are the consequences downstream that would occur in terms of statements or reactions or joint gain or some kind of outcome measures? And just as an example here, some papers that use a version of that. The top one had a code for information sharing about priorities and compare Japanese and American information sharing and see if that affected the results of the negotiation. Linda Putnam's work with Trish Jones coded for supportive arguments, substantiation, and compared labor and management and strategies used. The third one, codes persuasive behaviors, things like threats, and how does some personality characteristic cooperative orientation shape persuasive behaviors and outcomes. So that's what you're trying to do. And the process of coding is very expensive, very laborious, time consuming, can take months and thousands of dollars of coding time. And the question is, can AI make that coding process easier and less costly? So it's not going to replace, obviously, the full, stream of things that researchers do, but these two parts that are most laborious and most slow and costly, can we replace those with AI? So the first thing we had to think about is like, given that there's all these different coding schemes, what coding scheme do we use? It turns out that just lucky for us, right as we were beginning this, there was a paper published by Elizabeth Jackal, Alfred Zaris, and others, which constructed a master coding scheme for negotiation and tried to take all the different coding schemes and figure out what is the most essential, the most shared elements that you see across the key papers, and came up with a coding scheme. And we thought, well, great. So that that's the coding scheme we should use. It sort of covers everything supposedly. And this I don't want to go into in much detail, but this is that coding scheme, and there's 40 some codes there. When we began this, models can't really differentiate that. That's too much detail. And so we wanted to use this scheme, but we simplified it a little bit and combined some things. So in contentious communication combines, power, criticism, threat, and hostility. Substantiation, we combined a few things. And again, I don't think it's necessary to go in too much into the details, but there's a few buckets, and this was the coding scheme we initially started off saying we're going to try and see if we can do that coding for scholars. And one of the first things with AI is to figure out, do you need to fine tune a model, create a model or fine tune it? Or can you use what's called zero shot use of existing models? Can it code, the concepts you want to have it code without really adding anything or doing anything more? Is it ready out of the box? And so, most likely, we actually did some testing. Is something a positive statement? That's a phrase that is well known, understood in just common language, and that one you could do just fine with zero shot and don't need to fine tune. But something that like providing priority related information, that's something that is a technical term that really no model will know that unless you teach it to recognize it. So zero shot learning really would be insufficient, or zero shot without necessarily learning more would be hard to do. So our first strategy was to create ideal sentences. So we had this coding scheme from Negotiact, from Jackal and colleagues. And so we reduced it down to 19. Then we created between 30 and 90 ideal sample sentences for each code. That itself was a bit of a long process. We started off doing that just in our own heads. Then we used some AI to teach it a little bit, and then create more sentences, and then we double check it with ourselves, or human checking. So for example, providing positional information, here's 3 sentences examples. We would have about 90 typically for most codes. And so we created a total about 1,000 samples of codes. And we would train, the plan is to train on 70% of those and retain 30% to say, can the new model then accurately predict with the remaining 30% whether it can pick out what we intended that code to mean. All right. So for this, we first used a fine-tuning process where you take a base model, and then you train it and you create a new model. And that new model is the one that you would then ask to do the coding for you. So the prompt would go to the new model, and so we would train it with the training data, the 700 or so sample sentences, and then to ask the new model to code the remaining 320. And for doing that, we went into it using BERT from Google, and it's the bidirectional encoder representations from transformers. And what you see here is the confusion matrix. And the confusion matrix shows the diagonal line would say that code 1, and like here in the top corner, I think you can see my cursor, I hope, that's 11, where what we intended that sentence to mean was coded as that as that same code 11 times. If it's off diagonal, it means it missed. It didn't give the code that was intended. So you'd like to see as much as possible along that diagonal line. So we did okay. I got 61%. It's not what we'd ideally like, but that's what we got. And just about that time when we were doing it, another alternative emerged, which was Anthropic Claude 100K was a model that allowed for a lot of data to be added to the instructions so that you can give the training in the instructions rather than building a new model. So Claude 100K allowed 100,000 tokens, and we could send it a query, give it a prompt that included the 770 sample sentences and the codes we intended them to mean, and then ask them to learn that and at the same time code the additional 320 sentences. And the benefit of that, we suspected would be that the training data would be more top of mind of the model rather than teaching a bigger model, and our part would be a very small portion of that. So we did that. Oops. Where in this case you have the base model, the prompt asks the model to code the sentences, and the prompt also includes the training data, and it queries the base model. So Claude was the base model, and we did much better, much better. The matches, I got a typo there, but matched the intended codes 94% of the time, so nearly perfect. So this is what the confusion matrix looks like here. Really good. Almost everything's on the diagonal. It seems to be doing great. And we're thinking that all is good and happy. And I think that maybe probably when I talked 2 years ago at IACMR in Hong Kong, we might have been just at this point thinking we're really in great shape. And by the way, as an aside, for that conference, we just tested putting in Chinese versions of the same sentences and to see if it predicted the same categories, and it did. Just given its knowledge of general Chinese, it handled Chinese language perfectly well. But then we thought we needed to do one final check, and then we'd be done, which is to look at full transcripts uh, and 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 see if it did well on full transcripts. So Jackal and Zaris, were able to code some transcripts from their new scheme that they had just published, and we went in there, and the match was 32%. It was dismal. So all our plans were crashing and burning, and we thought, oh gosh, we're back to square one. And it's not surprising because when you go to a real language that is contained in a real transcript, people are using less perfect sentences than the ones we created as ideal sentences. They're uh, they're grammatically broken up. Um, they're not structured to be perfect examples of a code. It means there's lots of ambiguity. So it's a sloppier problem to really deal with real codes, real language. Um, and so this is, real conversations are not like sample sentences. All right, so what do we do? Um, One of the things we had to do is move away from the Negotiact coding scheme because that was new and there was not available yet, and I think there still probably isn't, a corpus of human coded transcripts using that coding scheme. Um, but what we needed was have to learn from a set of 50, 80, 100 transcripts that had been previously used in research and coded by human coders. And that's the long, laborious process that we're trying to, save people from having to do in the future, but trying to use that from when it was used previously. And so the idea is to take five, if we had a corpus of, 50 transcripts, take five of those transcripts and use that to train the model so that the model could see, each sentence and then see each code the humans had put on that sentence, learn that pattern, and then test whether it can do well in applying and duplicating the human codes on the remainder. So just to be clear, what it's learning is the way these particular coders at this time on this data set was thinking. It tries to reproduce the pattern of thought that's contained in that set. And one implication of this was we're getting away from a, supposedly all-inclusive coding scheme like Negotiact to one of the smaller coding schemes. And we realized there's no reason to have just one coding scheme. We can produce the model for any number of coding schemes that are contained in previous research studies. So in the long run, our plan is to have multiple codes available. We have two available currently. We have a third that's almost ready to be posted. So, but the challenge when we moved into this approach is, some codes may be interpreted slightly differently. So to say substantiation, maybe in one project, the coders were trained a little different than another place. So when we present a model, if it works, we'd have to make sure to show the users exactly how it was used in that project so you can know what you're getting. Humans include errors. So just because the humans coded it, and even if they had two coders agree, they can often be mistaken. They get tired, they get, they get annoyed, all the things that happen with human coders. So in some cases, there aren't training manuals for a coding scheme. And the other thing that we realized going in is, when we had our ideal sentences, we would create, let's say, 50 for each code. Well, in real coding schemes applied to real transcripts, something like, rejecting an offer maybe never happens in most transcripts. So you vary from having some codes that happen, 100 times across in a set of transcripts and maybe only happen 3 times. So you have to deal with that. And also different projects use different units of analysis. So the units of analysis is a really key problem in doing this coding. So the units could be a speaking turn. And so the sort of tan area I highlighted, when you see buyer, seller, it's very clear when a speaking turn begins and ends. But also it could contain maybe one sentence, but it could contain two, it could contain a long, long, complicated sentence. So coding the meaning of that turn is a little more ambiguous because it could have several meanings. You can code a sentence, which is that blue area, and you can see it towards the bottom of the transcript. And that's a little smaller, so and it's clear when it begins and when it ends, a period. But also what a transcriber has made into a sentence out of human language can sometimes be arbitrary. And then the third is a thought unit. You can take a sentence and break it up into subparts, each of which represents a thought unit. That's probably the most clear, but that's also a lot of work just to create the thought units to begin with. So just to give you a heads up, in a lot of the transcripts we were looking at, speaking turn is the most commonly used, although in most of those data sets, about 70% of speaking turns are really just sentences. So sentences are close to being are the modal kind of way of having units to analyze. All right, so let's go to the first model, and we built off of a paper by Aslani and co-authors from 2016. And we used Anthropic. We used Opus, which is their most powerful version. They had 75 transcripts. And in that study, they gave the students or the subjects uh, the, the, um, the simulation called Sweet Shop. So it's a negotiation about buying and selling, at related to a candy store. And they had speaking turn as the unit, 72% were one sentence. And you can see the coding schemes on the right. Um, single offer, single issue, a multi-issue offer, offer accept, offer reject, question, provide information, substantiation, and so on. So what we did is created a prompt, which we would have the 5 human-coded transcripts. We also kept an eye on where a given code might be too rare to learn from. So if a code occurred less than 15 times, then we added made up examples of that code just to have enough so that the model would have a clue as to what that code meant. Um, and we also realized in our early versions that information and substantiation often got confused, so we had some specific language about that. We learned that it worked better if we had to kind of say to the model, pay attention to who is the speaker, the buyer or the seller, pay attention to comments before and after, learn from the context and the flow. And it took a lot of work to get it to format the output in a certain way that's consistent. Um, and that gets important, especially because of some things I'll tell you in a minute. But that was a hard thing to do. And then we had to have the transcript. The transcript that we wanted it to code would also be in the prompt. We also realized in doing this that, is the question comes up, would the model give the same result every time? And the models aren't totally determinative. There's some variance that can happen. So what's the level of variance that's acceptable? Well, we decided the way to handle this was to run the analysis not once, but 5 times. And if we had, 5 times with the same code, perfect, we call that perfect consistency. 4 out of 5, high consistency. 3 out of 5, modest. And if it didn't do at least 3 out of 5, we would say the model does not assign a code. It's too unclear what it thinks to have an assigned code. So the first step of validation would be to ask, do the model's codes match human assigned codes for the test transcripts? So does the human assessment of that code and the model assessment, do they match? And we started off calling it accuracy. Then we changed it to the word match because it's not obvious that by the human code is obviously right. It may be wrong. So, but we care about the match, and we'll decide later about accuracy. So what we got were most of you'll see let me see if my cursor, it's 97% of the sentences that were coded, and we used sentences, matched perfectly. 5 out of 5, it assigned the same code. Among those, 74% of the time, the model code matched what the human had coded on that data set previously. Results were not as good for 4 out of 5. That was 2.5%. And then modest consistency, 3 out of 5. We got 100% just because the sample size was so tiny. And the kappa, assuming we treat the model and the human coders as like themselves 2 different coders looking at coder agreement, the kappa came out at 0.69. And then looking at a different statistical measure, 85% estimated observer accuracy. And we also checked whether the match levels were same for the first half and the second half of transcripts. It was possible to think that you'd have different dynamics in the beginning or the end of a negotiation. Would the accuracy be equivalent in the beginning and the end? And it was. So here you can see the RP, or positive reaction, was 26% of all the transcripts. So that's the most commonly used code. The least common code, used in 0.14% of the transcripts, was offer reject. In many transcripts, it never occurred at all, and if it happened at all, it would probably happen just at the very end. And also, you'll see that the model match with the human coders roughly looks pretty highly correlated with the quantity, with the number of the percentage, how frequently that code occurred. So you can imagine, as you have more examples, you have better, easier for the model to learn. And in testing out in the test transcripts, you have more chances to get past a given error. A larger sample size, you're going to get a more accurate measure. So that gives you a sense of how it plays out. And here's the confusion matrix. This is on the diagonal, where more of those exist. There are chunks that are off the diagonal. So here you have provide information where the humans coded it information and the model coded it summarize, and vice versa over here. So you had a fair number of misses in that case, but you can kind of see how information and summation can easily get confused. So someone says, because you want to eat ice cream, you don't want to be cold, because people normally buy ice cream in the summer, right? Because it's hot. Is that information about what their preferences are for the negotiator, or is it simply summarizing where things stand? You can see where it gets hard to differentiate. Or positive reaction and accepting an offer. That, is it simply saying yes to I that's true, or yeah, or is it saying I'm accepting an offer? And those tended to get confused. All right. So then the next question was, in those cases where there was not agreement, do we think that the model is right or the human is right? And so we started off thinking, well, the human is of course right, but then we thought, when we looked over those, what we called mismatches, it occurred to us that the model maybe was more right than the human in some of those cases. So we developed a process called mismatch analysis. And the idea is we would take a random set of 100 mismatches from the population of codes that our model had perfect agreement, 5 out of 5. And we had 2 new coders who would learn the coding system, and they would see what code was assigned by the model and what code was assigned by the human, but they didn't know if it was from the human or from the model. And we mixed them up. And we said, go through a voting process and think about which one is right. And what we got in this case was they agreed with the model 68% of the time, and they agreed with the human 32% of the time. So who knows whether the humans in these cases got tired, got lazy, kind of who knows what. But I think that allowed us to make an estimation that we think that about 91% of the model codes are likely accurate, even though the percentage that matched the human coding was less. All right, so that I think there should be pretty good confidence in the quality of the coding. Then we realized what we had done so far is to teach the model the coding system on one simulation on Sweet Shop, and then ask them to see if in other Sweet Shop simulations whether they could identify the right code. But in the future, the users aren't going to be using that same simulation. They're not going to be using Sweet Shop. So we had to, test it on other simulations that didn't have the same issues, the same language, the same names and buildings or whatever they were talking about. So we grabbed a set of other um, simulations, one transcripts from Cartoon, which was a different simulation about uh, sale of rights to cartoons, and a different one called Les Fleurs, um, about a flower shop negotiation. And we got 6 examples of each, and then we had to go and human code using the coding scheme that was used in our Model 1. And initially, these were transcripts that were coded for other projects with other coding schemes. So we had to go and can code them ourselves to create the human codes, and then do the analysis and see if the model codes would how much they would match the human codes. And we expected it to be somewhat worse because the situation in the language was a little bit different. So we call this step 2 validation, and the question is, do the model's codes match the human assigned codes for these 12 test transcripts that were different? In this case, we had perfect consistency 87% of the time, 5 out of 5. Among those, we had 65% match. High consistency, we had, in that case, 10%, 72% match, and 3 out of 5, we had 39% match. So overall, we had 65% match, which resulted in an estimated observer model accuracy of 79%. And we also checked to make sure that these results were equivalent in each of those 2 simulations. Then when there was a mismatch, we did an analysis of is the model or the human right? And this one we did a little bit differently, not just one or the other, but in some cases it was a clear choice where the human was right or the model was right. In some cases, you sit there and puzzle over it and say the human code is correct, but both are feasible. The model code is correct, but both are feasible. Both are equally correct. And that was 24 out of the 100 cases. There's a few cases where we thought neither one of them were right. I can't figure out how either one coded that. Or there's some sentences we couldn't understand. So that one would suggest that, about 21 plus 24 were probably, we could say that the model was at least not wrong. So the implication we take from that is for about half of the mismatches, the model is probably right, which brings us up to about maybe 88% or so likely accuracy of the model code. And for those of you who've ever done this kind of coding, that level of accuracy would far exceed what you'll typically get from humans. And we also had some technical challenges along the way. Early on, we'd have the model kind of go and tell us what the code was for each sentence, and it would change the sentence and correct the grammar because it sort of automatically did that, which would change the meaning in some cases. And we had to add some things to the prompt to make it not do that. And sometimes the format would come out in different ways. You want to have it, with the result, the code. And especially since we were doing it 5 times and adding up the results, we had to have it in a format that it could process and combine the results. And And then there's some aspects of how much variation it produced. There's also a problem of laziness we ran into, where it would sort of stop working at some point, which is a known problem with some of the models. And then also, when you build a whole validation scheme around a given model, you sure hope that the company keeps producing that model in the future. Because, if you want to try it out on a new AI model, you've got to go through the whole validation process over again. So indeed, we've had people say, "Oh, can you give us the prompt and we can just go run it on Llama or some other model?" You could do that, but it's not validated. And the whole point of us validating it and providing all this data is to make it arguable, support you if you use it and go to a journal and you want to publish and you say, this is an acceptable and validated and carefully done process so you can believe it and it's worth the journal accepting. If you take our prompt and go take it off to Llama or somewhere else, you have no idea or no validated idea of what is right or wrong. So where we stand now is um, we have a website. That's the website, AI Negotiation Lab, and you go there, and there's two components in the bottom. The one on the bottom right is not really up and running yet. If I have time, I can tell you some about that today, or might not get there depending on how the conversation goes. But if you click here on the AI supported transcript coding, and it takes you to well, I skipped one page, but it takes you to a page um, which is gives you a choice of models. Right now, there's Model 1 and Model 2. And when you get there, it will kind of give you a reference to a paper which you can cite with all the validation data if you need to for a publication. It goes into the coding scheme used, which is also which is shown in great detail with examples, definitions. Then it tells you about the coding process, how to do the coding yourself, or how the coding is done. And it has all the validation data, which I've just gone through in briefer form. There's more detail. It tells you how to format your transcript. It's basically an Excel file where you put a row, the speaker, buyer, seller, and then in the second column, put in the sentence or whatever you put in. You can put in whatever you choose, a speaking unit or a thought unit, a sentence, a speaking term, whatever you want, and then a way to submit your transcript. And so to submit your transcript, you go to this page. And by the way, we've updated this slightly. I need to um, update this slide because we've done it something a little bit differently. I can explain later. But you drag and drop your files and you submit it. And after about 10, 15 minutes, you can access the coded transcripts. One thing we do ask, we realize that in some cases costs can be substantial, a lot less than it would be doing it human coding, but it still costs us to pay Anthropic to process the analysis. So for Model 1 and Model 2, one uses Opus, which is more expensive. One uses Sonnet, which is less expensive. We just couldn't get Model 1 to work effectively unless we used the more expensive Opus. So for example, 50 80 row transcripts in Model 1 would cost about 400 US dollars. Model 2 would be around 40. But luckily, NTR, which supports negotiation research and also has supported this whole project, uh, offers a small grants to cover these costs. And you can, there's the link to their website, and you can put in your name, email, and your affiliation, and it will ask you about your project, which model you want to use, what your kind of research ideas are, and then if approved, will send me the funds to cover whatever the analyses you plan to do. Okay, so that's available. Um, and hopefully that's a process that is useful to people and um, opens up the possibility, even though it might cost, you know, $400, $500, that it doesn't cost you 2 months and thousands of dollars. So let me stop there. I've another section I can talk about and switch gears, but let's start, and we may just do a bunch of discussion about what I've shown so far and see if there's any issues or questions that people have.
Okay, thanks, Ray. So if you have any questions, you can just you can either type in the chat box or you can just open your video and ask.
I see that Shuhui uh, posted the link
Yep.
uh, under messages. So Shuhui is doing most of the work building the models, and he's the guy who knows kind of the technical side of what's going on better than I do. Someone said link again. So where is the data stored that is fed into the system? Uh, because it is in context learning, it is not incorporated into the model and retained by Anthropic, and it's brought into an analysis, it's processed, it's spit out, and it's forgotten. So after each analysis, the input you have, which would include, you know, the prompt and the transcript that you're having it code, all of that is forgotten at the end of each run. So in fact, it's not stored. So how does researchers cope with the discrepancy between human coders and AI model to get a consistent code? Um, the ultimately what you care about is truth, right? And so, you know, what prior to all of this, what you had is the presumption that human coders represent truth. Now, I mean, there's a set of rituals we go through to convince ourselves that the human coders know truth. Anyone who's ever done any kind of coding like that recognizes how uncertain some of the coding is, how problematic it is. Uh, it's not, yes, we go through iterator reliability. You know, if you've ever trained coders and you say, you know, coder one and coder two, you know, the first pass through it, they often have very different ideas about the codes. Then they have a discussion and they come up with agreement, um, and you hope that they've got the same idea. But that is an inherently imperfect thing, and so let's not fool ourselves into believing that that's necessarily the true. So that the model is doing is reproducing, learning some of that all as much as it can. And so where there's an inconsistency, I think we've dealt with it by saying, you know, asking the question, is the model right or the human right? If you're contending, you know, which one of these two are possible. And as the second set of mismatch analysis I presented shows, even doing that, you know, there's going to be some clear-cut cases. You know, model is like clearly wrong. you know, who knows why. The human, clearly wrong. And then there's a bunch where you'd say you could sit there and spend an hour debating between two coders, and you maybe end up with one result because you kind of have to by rule, but they could have easily come up with a different reasonable outcome, because and as we go from the ideal sentences where a sentence is structured just exactly to fit a concept, language doesn't happen that way. So I'm hoping that the way we've presented in our papers, that it's convincing to reviewers. But reviewers go based on norms as much as based on what's actually right. Um, is it suitable only for negotiation data? The coding scheme um, is is designed, yes, for negotiation data. If you look at the codes, if there's any reason why, it might be applying to mediation. Um, you take a look at the codes if you want to look at them and see if it might be useful for you. I also know, I wish I had it off the top of my head, but there's a woman at Wharton who's created a more general coding scheme that's automated that needs Python to run. And let me see if I have, um, I might be able to put, her, it's a PhD student, Emily Hu at Penn at Wharton, who's got a coding scheme which is much broader, but also requires more programming language. And I think Python, you have to be able to handle that. So if you want to contact Emily Hu at Penn in the PhD program, she has just built a program that does a broader range of coding. If we run um, multiple rounds of AI model, is there a possibility to teach AI model to learn from and imitate human coding process? I wish I'd love to hear more on that idea. I don't quite get the idea. Um, so this is Lu Dai.
Yes,
Can you?
Professor, my question is, if we run multiple rounds of AI model, then AI model will learn from our coding process and thinking. So the difference between human coding and the AI model coding will be reduced.
Well, I mean, that's exactly what we're doing. So there's human coding process, which is the historic transcripts used in these prior projects. So Aslani et al. And we have the documentation of their coding process, which we then feed into the model, and the AI is learning what their coding process is, and then trying to reproduce that um, as it looks at, and then I think that's exactly what it's imitating the human coding process. That's exactly what it does.
All
Um,
right. So the AI model is different from the human wisdom. So this is quite a different coding agreement process, just as the same way between the two coders of the human coding. I mean, the one person and another person make agreement in the coding process is quite different way, just as one person and AI model get agreement process.
well, okay, so when the people do two humans,
Yeah,
there's a process. They go learn the coding scheme. They they each apply it, and then there's a conversation that goes on between the
right,
two humans,
right.
typically, and then they kind of come to agreement where they disagree. They come to agreement, so that there's a conversation process, with the model and the human. In this case, there's no ability to get those humans back and talking with the model. Those humans did that, 8 years ago. And so which makes it harder to get agreement. So usually the human to human agreement, you only get, though often you'll see reported, you know, 0.8 or something high. Most of the time, if you know what really look carefully what happened, that only happened after lots of conversation and people changing their minds and convincing each other. And then oftentimes what they'll have is the two coders, once they come to agreement, they trust that that will hold and they send them off having only one of them code a given transcript to be more efficient. But there's not, so that kind of makes the score look quite a bit higher when you have humans who are, trying to coordinate between each other. And so it's tougher to get good match with the model and that human code. But I think that makes the relatively high level we get of match pretty impressive. I hope.
Thank you. Thank you.
And then you see, what is the difference between your model and ChatGPT? Could ChatGPT run the same task? Okay, so one is ChatGPT is not set up like when we have our input. The reason we use Claude is that we give it like 30 pages of input to doing context learning. ChatGPT can't take 30 pages of input. And so, even as we've gone along there, Claude 100K kind of expanded in its capability so it could take more and more and more. And luckily that happened because to make it work, we had to have more instruction, fix this, fix that. So ChatGPT is not built to allow gigantic amount of inputs the way we're doing. There could be other models that you can do that now. I'm not sure what the token input limit is, but you could take it and run it on other models. And when we actually tested it out, we tried other models and Claude did the best, but it keeps improving and changing all the time. So maybe some others do better. But if you take the prompt that we'd be happy to share with you, and you go off to Llama, it hasn't been validated. So you could get it to produce a result, but you'd have to go through enormous amount of time and effort and money to revalidate everything. And that's where all the effort and cost and time occurred for us building this. So that's really the constraint is there's two parts of the constraint. One is you have to go through all this validation process. And the second is that we've chosen to have, run it 5 times and then and code that into level of agreement, of consistency across the 5. We think that's important to do. That is built into sort of our side of processing. It's not something, I mean, you'd have to do that all manually if you did it off with another model, which could be done, but it would be really laborious. But the more important one is it hasn't been validated. And indeed, even with Claude, if you use Claude Opus versus Claude Sonnet, you get different results. So our results really only are validated for the model that we list. So the one that's on Opus, you kind of have to use Opus because that's what all the data comes from. And the one that we have using Claude Sonnet, you have to use Sonnet because that's where all the data is validated. Okay. All right. Any other questions? Let me just see how we're doing in time.
We still have time, and we have missed 2 questions. One is from actually Andrew Wang.
Oh, I missed that one. Okay.
Yeah. So is it possible to tailor the coding model such that we can code some variables that are not included in the current coding scheme?
No. The reason is again, we're learning from the human, from the corpus that we received from people who are helping us from a prior project. And we're asking, and the model is learning that set of humans' way of thinking and how they coded. But if you add a new code in, there's no data for us to build off of. So that didn't exist in the corpus of the transcripts we had. So we would have no way to, and so, if you had a coding scheme that you went ahead and provided us with 70 coded transcripts using your coding scheme, we'd be willing to work on building the model if the coding scheme seemed generally interesting to a wider population. And in fact, we've offered that to people, and we say that on the website. If you have a very different coding scheme that that you've already done a whole lot of work on and are willing to let us learn from, we can take that and see if we can build a model that reproduces that coding scheme. But that takes a fair amount of work. It's not like just adding one variable in easily, but you'd have to, have it, 70, 80, you have to have a lot of examples in the training data set, and you'd have to have a lot of examples in the testing data set to see if it can work. But that's a big project. And it probably takes us, 6 months to go through to build a new model of work. And when we have one of them where we did that, we went and we spent 6 months and we figured that one we just couldn't make work, so we had to really dump that and go on to another one.
Yeah, thank you very much. Thank you very much, Ray. That's really helpful.
And what was the other question I missed?
I think that's from JX Lin. Has your group faced pushbacks?
Who are against using LLM? Well, no. There's a couple. I mean, there are LLMs that are being used a lot in coding, but more often they're very narrow. If you're going to say I'm looking for anger, and you can kind of if you have one sentiment, you're trying to teach it. And Emily who I just mentioned has ways to do that. So there's lots of people doing other sorts of coding schemes but I'm not sure. I'm assuming that they've gotten through review processes before. I'm not 100% sure, but I'm pretty sure there's a whole lot of it going on. It's too early to know whether this particular application of an AI model for coding will get through the review process. That's why we posted the papers that gives lots of detail on every aspect of how we coded, that I'm hoping, it's not perfect, but it's pretty good. And anybody who's really gone through the human coding side would probably see this as equally or more strong than that traditional human coding side. But it's still to be tested. I think the people who are most interested to try this, or PhD students have come to us a lot because they don't have the same budget for doing coding. People who've had gigantic data sets where it's just simply not feasible. I mean, if they were forced to do a human coding, it would just never get done, and impossible. So they're willing to take the risk of proceeding and testing out how the review process goes. So the other question, yeah, I'm looking at Zoe. Thanks for sharing. I have a similar question about ChatGPT. We prompted ChatGPT with a code book and then asked the chat to categorize human scripts accordingly, and we found AI, human RA consistency. Great. I mean, I kind of would need to see a little bit more about what you're doing. If you could send me your results, I'd love to know about it. Um, um, Categories, definitions, examples provided. Yeah, I'd love to see how, because if you can get away with doing it with ChatGPT, and can validate it, that's a pretty efficient way to do it. Uh, for our coding scheme, we weren't able to get away with that. Um, yeah, because you can't give it nearly as much data as we're giving it. But if you're getting 0.84, that's fantastic. Um, can it read different languages? Yes. My understanding is that it can. And we haven't tested it recently on our published model. We did earlier where we put in, okay, there's two levels of difference with language. So one is if you say, how much is that price on that book? And you translate that into Chinese and you look at the code it would be assigned. We were finding the code assigned would be the same for Chinese or English. It would now whether there's cultural things involved in Chinese that would shape how you express something in a different way. It's not clear that it would recognize the cultural differences, but in terms of like literal meaning, it actually it will read the words in Chinese and it will process it as if it understood like the translated version of that and connecting it to our database of the training sample that we used in building our model. So I think it should. I'd love to see some people try it and let me know. Just put it into the Excel spreadsheets and by the way, it's set up now so that if you want to go and try, 3 or 4 or 5 Excel spreadsheets with transcript data and see what it looks like, you go ahead and try that just to see if it works. If you're gonna use it full blown, where you're gonna do 100, spreadsheets or 50 spreadsheets, then we ask you to, cover the cost. And again, NTR most likely has the funds that support covering that cost, and it can be minimal depending on how big the data set is. And there's some guidance on the website about what the cost estimate would be. But I think it should work in Chinese.
Great. It seems that you have answered all the questions. We still have 5 minutes. So
I have another bit of another side of things I can just show you for 5 minutes. Let me kind of share my screen again. But I wanted to really get into the coding completely before. We also have this idea of which we haven't implemented yet, and it gets more complicated, of a quasi-subject pool. Can we produce a model which would incorporate a broad knowledge of how humans interact in negotiation? And so we were able to collect from scholars who are helpful about 1,870 negotiations of negotiation and dispute transcripts. So it's a fairly big corpus of negotiation data. And can we teach it, a model? Can we take a foundational model and let's say GPT-3, train it with this data, and then have a new separate model, which can be, in effect, a subject pool representation that can be queried for any number of questions. So we have a bunch of transcripts from all these scholars coming from different countries. We have metadata on, year data collected, simulation versus natural, integrative, distributive negotiation, and so on. And what we don't have is outcome data like, the final cost or price or deal. But you might be able to ask questions of this new model. If you look for cases of active listening, what are the immediate or lagged effects that occur after active listening? What statements typically precede active listening? And we can imagine a strategy where you say, like, what response does a given statement trigger in the population? And you give an instruction to the model. Person A says, I hate you. Person B says, and the model has to give a reply. Or model person we insert says, why do you want this from me? And you can see it, produce a variety of responses and maybe run it 100 times. So you get 100 responses that you can code like we would code human responses and look at patterns of that set of results. You can go in and have tell the model person A says, person B says, person A says, person B in the negotiation. And you can rig it to give positional information or give active listening and see if the model produces different results after hearing active listening or after hearing positional information. Or you can vary the prior language. So if you say, why do you want this from me? Is that preceded by, I've been trying to find a way to resolve this, or you've been opposing everything I say for the last 4 hours, and see how does the prior statement affect response to the statement. So that's just an idea. I won't go into there's a whole lot of other technical details. And we're just sort of beginning to get back to that project, which is a whole different angle on using AI as a research tool. I'm not sure we'll get there, but Daniel and I are working on seeing if we can puzzle through this. And in AI speak, it's like creating an agent that represents a subject agent, an experimental subject agent. We're not sure if we'll be able to succeed. That's still pie in the sky, but hopefully the coding model will be useful to people right away.
Okay, great. So thanks, Ray, for sharing this great work and also sharing this platform website. I think many people are interested in have a try. So
And if there's any questions about it, just send me an email, and any problems with it or issues, just let me know and we can figure it out.
Yep. And also thanks everyone for participating this webinar. And hopefully that Ray, you can make your trip to Xi'an. Then that anyone who are interested in this topic can have an engaged discussion with you.
Sounds great. Well, it's great to see you, Wei.
It's great to see you. Okay, I think that's all for today's webinar. Our next one will be held in May. That's a macro track. And our next micro track will be in July. So thanks again, Ray, for your wonderful